Hi everyone, I'm Deepak. I'm a postdoctoral fellow at Indian Institute of Astrophysics. First of all, thanks to the organizers for giving me this opportunity. So I'll be talking about something quite different from what you have been hearing for the whole week. So instead of fast radio bursts, I'll be talking about fast X-ray transients. And so these are the transients these days have been detected in the Einstein probe mission. And this is a work which I'm doing in collaboration with a lot of people, especially with the growth collaboration and also with Arvind Balasubramanian here. So the first question is, what are fast X-ray transients? It might not be as fast as fast radio bursts. So these are X-ray transients, as the name suggests, fast X-ray transients, which last over the time scales of few hundreds to few 10,000s of seconds. And the origin is not very much clear. And there have been about 140 plus extragalactic fast X-ray transients which have been discovered from Chandra, XMM Newton, also from Swift and Rosetta, and recently from Einstein probe observations. So one thing to note is that most of the pre-Einstein probe era fast X-ray transients, they have been found from the systematic searches in the Chandra and XMM Newton archival data. So people go and look for the fast X-ray transient and they find these kind of extragalactic FXTs. So this plot here shows two Chandra detected fast X-ray transients in comparison with other different kinds of X-ray light curves of different other transients like short gamma reverse, SN 2008D, where y-axis is flex and x-axis is time. So this figure is a very rough parameter space being occupied by the fast X-ray transients or FXTs. So these FXTs occupy the region which is also occupied by different classes of other transients. So, and the peak X-ray luminosity varies between 10 power 42 to 10 power 52 ergs per second. So it could be a heterogeneous population that we are talking about. Like we heard about LPTs, it's like a phenomena. So similarly, it's a range of heterogeneous population of transients. And so the question is, what are its possible origins? So these days we have seen a lot of fast X-ray transients being associated with long gamma ray bursts. So that is one of the possible origin, because with EP Einstein probe mission, we are seeing a lot of FXTs which are associated with long GRBs. I will discuss about long GRB association a bit more in the later slides. Another progenitor is a white dwarf intermediate mass black hole TDE. So when a white dwarf gets tidally disrupted by an intermediate mass black hole, it produces X-ray photons, which is something which we might be seeing as fast X-ray transients. And because of the compactness of the white dwarf and the comparatively lower mass of the intermediate mass black hole compared to that of the supermassive black hole, the time scale associated might be short. So that might be one of the progenitor for this fast X-ray transients. And in one of the FXTs from the Chandra, XRT 005 and 9, we even saw two precursors before the main event. And that time scales are also agreement with a void dwarf in an eccentric orbit around an intermediate mass black hole. Another possible progenitor is a binary neutron star merger. So some of the host properties as well as the luminosity constraints, this points to the binary neutron star origins in some of the fast X-ray transients. And for some of the FXTs, the host properties very well match with the binary neutron star origin. And in these days, as most of the transients are associated with magnetar, there is also a crude model which is also for fast X-ray transients, where magnetars act as a central engine. And you can see there are three zones, a jet zone, free zone, and a trap zone. So if you're viewing in the jet zone, you will also see the fast X-ray transient along with the GRB. And if you're in the free zone, basically it's off axis. So you might not see the GRB, and then you will see the X-ray transient as a whole. But if you're in the trap zone, you will first the X-ray photons are obscured by the ejector itself, and later as it becomes optically thin, we see partial light curve of this transient. So in this is a crude model which could explain the light curves of some of the FXTs. Another possible progenitor is a supernova shock breakout. So in case of SN 2008D, we saw a fast X-ray transient associated with one of the supernova shock breakout. So that was the interesting thing was that they were looking for some other supernova, 2007 UY, and then this accidentally popped up. So it was a lucky detection in that sense, and it was the first time we had an association with a fast X-ray transient and a supernova shock breakout. and it had a peak luminosity of around 10 power 43 x per second. And one thing to note is that from the models, it predicts that the peak extreme luminosity of supernova shock breakout cannot exceed 10 power 44 x per second. So that is one constraint for this supernova shock breakout origin. And we see a diversity of X-ray luminosities in the case of FXTs. And so before Einstein probe era, what was the counterpart? I mean, as I mentioned, most of the FXTs before Einstein probe was found through the systematic searches in the archival data. And so the prompt follow-up was not there. And so hence, there was lack of counterparts except for in the case of SN 2008D. And the best case scenario was in the case of CDF-S XT1, which is Chandra Deep Field South X-ray Transient 1, where there were observations 80 minutes after the FXT itself, constraining a limit of 25.5 in our band. So with the absence of counterparts, what is a possible way to understand its origin or to constrain what is the nature of this FXT? So the best way is to look into the host properties. So as there have been a lot of discussion on the host properties of FRBs, so similarly we have been trying a lot to constrain the nature of the FXTs by looking into the host properties. So this is a case of XRT 210423, which is again a FXT detected from Chandra data. So we were able to look into the region within 2 weeks, but we couldn't find any counterpart. But so this is just to give an example. So we have 3 candidate hosts in that region, CNE, CX, and CW, where we have a spectroscopic ratio for one, a photometric for another one. And you can see that there is a very faint, might not be visible, the CX. It's a very deep optical limit of, optical magnitude of about 26 mag in G band. So by looking into the host properties itself, like star formation rate, mass, and also the host offsets and all, we are able to connect it with what progenitor it is, or rule out some of the progenitor in some cases. So that's one of the way to, before the Einstein probe era, that was the way we were constraining the nature of the FXTs. So then comes the Einstein probe mission, and this is a mission from the Chinese, led by the Chinese Academy of Sciences. And the Einstein probe mission is completely revolutionizing the way we are seeing this the high energy transients, because it's throwing at us all different kinds of transients, including TDEs, collapsers, like that too, not the standard collapser models, all different kinds of transients, also even BNSs. We have not found any supernova shock breakout yet, but it's a mixed class what Einstein probe is throwing at us. And it's a wide field survey in the soft X-ray band, and it has 2 science instruments, which is wide field X-ray telescope and a follow-up X-ray telescope. And EP provides accurate FXT positions within 10 to 15 minutes via GCN circulars, which help us to promptly follow up and get the multi-wavelength counterpart associated with it. That's the best part about EP. So we have information about the localization, which is to few arc seconds, and hence we are able to locate the counterpart. So just to show the diversity of light curves the EP provides, I'll just give you one example. So this is EP 240448A. So you can see that this is the optical counterpart. And so you can see that it was detected at 21.2 mag. It had a sudden decay in the magnitude, and then a steep rise in the magnitude in the phase B, followed by a decay again, a short rise here, and again a decay. So one interesting thing was that, in the phase B, it shows very much properties very much similar to that of this luminous fast blue optical transient. It's another class of transient. So basically all of them are getting mixed up in these days. So and they also have a very blue spectrum in the phase B, and in type C, the spectrum shows the properties of type 1C, which is basically associated with the long GRB progenitor. So this is again in the lower panels, they're comparing it with the 18 cow, which is an F-bot, but at the later times it's not matching, but also with 98 BW, I think it's a type 1C, and you can see that it's matching for a type 1C light curve. Yeah, so one way to explain this, crude way to explain this light curve is that, so you have collapser, and then you have a cocoon which is dominating in the first phase, In the phase B, basically the jet is launched, it interacts with the circumstellar medium, and the afterglow is produced. So that could be phase B, and then phase C is basically the radioactive decay of the supernova itself. So this is one crude way to explain this light curve, but it's very difficult to explain this kind of peculiar light curves. So I'll just briefly discuss some of the efforts which we have done to follow up a couple of fast X transients. One is EP241107A. So in that case, there was no gamma ray burst detected at all. And we got a Keck spectrum at a redshift of 0.456. And we have extensive follow-up observations with GIT, SCT, SOAR, VLA, and GMRT, also with AstroSat. I forgot to put it down here. And it has, at that distance, it has a peak luminosity of 10 power about 3.4 into 10 power 48 ergs per second. And the second one is 240801A. It's so the Jiang et al. Reported that it's associated with a very faint GRB, and it's at a distance of 1.673 redshift, and the peak luminosity is of the order of 10 power 50 ergs per second. So in these two figures, we are basically comparing the optical counterpart light curve and the radio light curve with the non-classes of other transients. So you can see that these two are in agreement with the larger population of afterglow seen in GRBs. And here, we had two POC of GMRT observations for 240801A, but it only gave us upper limits from UGMRT. And for 241107A, we have again two upper limits in band 4 and band 5 for 241107A, but we have a detection in VLA. That again agrees with the long GRB kind of and progenitor or the region, the parameter space occupied by these GRBs. Other thing what we did was to look into the host properties. So we kind of did the SED fitting with the available photometric data. And there's not much we can infer from this plot, but like one thing which you can see is that it broadly agrees with the short GRB and long GRB kind of host scenarios. That is the only thing which we could infer from this analysis. And this is also not very robust because we only use very smaller number of photometric data to infer this host properties. But again, it tells us a story that it's more in agreement with the short GRB as well as the long GRB kind of like the host properties. Then we went on to do the afterglow modeling with Afterglow Pi, where this is basically the synchrotron modeling, and we have used all the multi-wavelength data which we are having along with the data available publicly. And thanks to the radio data, it helped us constrain the model better. So this is a best fit light curve for this 241107A. And the jet properties which we inferred was it has an EKI, so isotopic kinetic energy of 10 power 51 erg, which is and a core angle of 15 degrees, viewed almost on axis at 9 degrees. And for the beam corrected energy, it's around 10 power 48, which is at the lower end of cosmological GRB. So we, with the absence of the gamma ray burst is absent. Also from our modeling, it inferred a low energy for a beam corrections, and also for the on-axis geometry, we infer that it's a intrinsically faint GRB, that is 241107A. So this is my final plot where we compared the 240801A with the 241107A with the landscape of all the FXTs we are having. So these are the Chandra and XMM detected FXTs, and these are the EP Einstein probe detected FXTs. So you can see one clear pattern here. This Einstein probe is more sensitive towards luminous high redshift galaxies, and most of them are associated with collapsar progenitors. But some are TDEs or some are binary neutrons or mergers. And yeah, so we might be talking about two different populations of FXTs. But one important thing to note is that because in most of the cases, in case of Chandra and XMM Newton, the constraints come from the host by looking into the host. And if the host associations are not very well constrained, that could be giving us a wrong population, because that would show us a different redshifts and hence a different luminosity. So that is one thing to keep in mind. So with that, I'll summarize. So FXTs exhibit all diverse properties and is believed to be originated from different kinds of progenitor. We looked into EP24080A and 1107A, and they are consistent with the GRB origin. The absence of gamma ray emission, the inferred on-axis geometry, and the energetics which we derived for 1107A, which shows that it's an intrinsically faint GRB, and EP is finding a lot of significant number of FXTs, and prompt and multi-wavelength follow-up observations are very much essential to characterize what's the nature and to better constrain what progenitor it is coming from. Thank you.
Okay. Questions for Deepak?
Hey Deepak, in this 50 or above FXTs discovered by EP, at least some of them I believe are also seen by BAT or GBM.
Yeah.
So how does the duration compare in this population between the gamma ray instruments and the EP? The same burst, how the duration difference?
From the Fermi-Lat or like GBM and the EP?
Duration versus EP duration for the same event.
Yeah, so I mean, for the gamma part, it's much shorter, like compared to that of EP. But the time at which it is being detected, in many of the cases, the EP detection is like coming first and then followed by a GRB. So there is that kind of a delay in some cases. Some cases they have there is a gamma detected at the same time as of the Einstein probe detection. So yeah, it's different for different kinds of FXTs actually.
Any explanation for this?
Yeah, I'm not sure if there is a clear explanation for that. I'm not aware of it. But at least I think even in case of earlier GRPs also, at least in some cases there was an extra emission before the gamma itself. That's what I understand. So it's not very clear what population.
Any further questions for this? Anything from online? Okay. If not, let's thank Deepak. Thank you.